Today we're looking at section 11.2 on events involving not and or. Properties of probabilities. Let's just review some of the things that hopefully you have picked up from section 11.1. Let E be an event from the sample space S, that is, E is a subset of S. Then the following properties hold. First of all, the probability of any event E has to be a number between 0 and 1 inclusive. So 0 is less than or equal to the probability of E, which is less than or equal to 1. The probability of an impossible event is 0. The probability of a certain event is 1. Okay, now we're ready to look at what is called the complements rule of probability. The probability that an event E will occur is equal to 1 minus the probability that it will not occur. So the probability of E is equal to 1 minus the probability of not E. And there are a couple of ways to indicate not E. One way is to use the accent mark, I guess you could call it, or the prime mark. Another way is to draw a bar over E. So you may see that both of those notations. So I want you to be aware that you may see it looking like probability of E is equal to 1 minus the probability of not E. Both of those notations are used. Now, what basically this comes from is the fact that the probability of E plus the probability of not E is equal to 1. So the two are what we call complements, since the sum of their probabilities is equal to 1. So let's look at an example. It says a single card is drawn from the standard deck of 52 cards. What is the probability that the card is something other than an ace? So the probability we get something other than an ace, or we could think of it as not an ace, would be 1 minus the probability it is an ace. So in our deck we have 4 aces. So that means the probability of getting an ace would be 4 out of 52. That reduces to 1/13, and 1 minus 1/13 is 12/13. Remember that 1 we can represent as 13/13 minus 1/13. 13 minus 1 in the numerator is 12/13. Okay, so now I have one for you to think about and give a try on. A single die is rolled. What is the probability that it is something other than a 1? Think about the complements rule. How can we apply that to solve this particular problem? Okay. So we want the probability that it's not a 1. That's going to be 1 minus the probability it is a 1. And what is the probability of rolling a 1? We know that's 1/6. So again, we know 1 is equal to, in this case, dividing it into 6, it would be 6/6. And so we end up with 5/6. What happens is that sometimes the complement is easier to count than the probability we're looking for. So we just take 1 minus the probability of the complement. Okay, the general addition rule of probability says if A and B are any two events, then the probability of A or B is equal to the probability of A plus the probability of B minus the probability they both occur. Okay, and you might wonder, why do I have to subtract that off? Let's see if we can figure that out from the example. It says in example 1, a single card is drawn from a deck of 52 cards. What is the probability that the card drawn is a face card or a heart? Okay, a face card or a heart. So the probability we have a face card is 12 out of 52. Remember, that's the Jack, Queen, and King. So 3 cards times 4 suits, there are 12 of them. Okay, the probability we have a heart, there are 13 cards in each suit. So the probability of a heart would be 13 out of 52. But what happened? What did we do when we were counting them? Let me draw a little Venn diagram. Whoops, let me get my pen back. So we have the face cards, and we have, and that's not going to be big enough. Let me start over here. Enlarge it just a little bit. Okay. Alright, we have the face cards. That includes all of the kings, queens, and jacks. And then we have the hearts. So in the overlap region, we'd have the 3 face cards that are hearts. That's going to give us 10 remaining hearts out here, and the 9 face cards from the other suits. So what we see is when we say 12 for the face cards and 13 for, what have we done? We double counted the 3. And that's why we have to subtract off the 3 over 52, because of the fact we counted 3 of the cards as both face cards and also as hearts. So that's where we get into trouble. So those 3 have to be subtracted off. And when we do that, we get 22 over 52. We can reduce by 2 in the numerator and denominator. We get 11 over 26. Okay, so example 2. This is for you to think about. We're drawing a single card. What is the probability that the card is an ace or a red card? Pause the recording and see if you can come up with the answer. Once you think you have the answer, then go ahead and restart it, and we'll go through the problem together. Okay, hopefully you have come up with an answer. So what we need is this particular formula. Okay, so the probability we have an ace is 4 out of 52. Probability we have a red card, half of the cards are red, so that's 26 out of 52. And how many cards do we double count? We double counted the red aces, and there are 2, a diamond and a heart. So 30 minus 2 gives us 28 out of 52. 4 will go 7 and 13. So we reduce that down to 7/13. Hopefully you got that one right. Alright, and one last point I should make is the idea of mutually exclusive events are 2 events that cannot occur at the same time. Okay, for example, if you're drawing one card from a deck of cards, then drawing an ace and drawing a king would be mutually exclusive. You can't draw one card that is both an ace and a king. So they're mutually exclusive. That means they cannot occur at the same time.